Hello everyone, I am Asfahan Shah. I am a third year undergraduate student of computer science and engineering. Today I am going to present my paper titled A Comparative Study on MFCC, i.e. Mel Frequency, Substrum Coefficients and the Fundamental Frequency based Speech Emotion Classification. This paper was authored by me and co-authored by Dr. Tanmay Bhowmik. The presentation will briefly cover the following points which are shown in the table of content. First, the presentation will cover the introduction. After that, it will cover the two features which are used in the study in detail, that is the melt frequency spectrum coefficient and the fundamental frequency. After that, the presentation will cover the methodology which was used in the study. After that, the presentation will cover the results and then its analysis and the final conclusion of the study. Now coming to the introduction part. Humans are emotional beings by nature. They have the capability to express various kinds of emotions like anger, happiness, sadness, etc. For human-computer interaction, emotion detection and recognition by a computer becomes an important task. Mainly, these emotions are expressed by facial expressions. But as human grows, an individual learns to control one's expression, thus making emotion recognition a challenging task. Emotions can also be detected by using audio features of the speech. Speech emotion detection is one of the emerging domains in artificial intelligence and machine learning. Speech emotion recognition is a process of detecting an individual's emotion using the speech. This is effective as the audio features like tone, pitch, etc. changes according to the mood or the emotion. A speech emotion detection system mainly consists of two parts: pre-processing and the classification. The pre-processing part consists of extraction of audio features like pitch, mel frequency, spectrum coefficients (MFCC) from the given audio files. After extraction of features, these are then normalized. After the normalization, then comes the part of the classification. Classification is done usually by various machine learning algorithms like support vector machines, decision trees, etc. One of the most important aspects of any classification algorithm is the choice of the features. Features should be chosen carefully before the training and testing of the model. Speech emotion detection is important and has applications in various fields. One of them application is in the field of medical science, where it can be used to evaluate emotional health of a person and can help in early detection of mental disorders like depression, post-traumatic stress disorders, and suicidal tendencies. Each emotion detection can also be used to improve human-computer interactions, which in turn improves various applications like smart home appliances. Speech emotion detection can also be used to improve customer feedback systems. In this study, we have used fundamental frequency and mel frequency spectrum coefficients for speech emotion classification. In in this study, we have compared both the results of speech emotion classifications both from the fundamental frequency and mel frequency spectrum coefficients. Now, before going into the methodology and results, we are going to first discuss about both of these features in detail. Now, coming to the Mel frequency spectrum coefficients or MFCC. Mel frequency spectrum coefficients are audio features which are commonly used for speech recognition applications. MFCC is computed by first taking fast Fourier transformation of the sound signal. After that, a Mel filter bank is applied to this transformation. Further, a logarithm is applied. The final process is to apply a discrete cosine transformation on log Mel filter bank. This results in formation of number of coefficients which are equal to number of filters in Mel filter bank. This process is illustrated and summarized in the following flow diagram, in which we apply a fast Fourier transformation to this signal, then Mel filtering and a logarithm is applied. After that, a discrete cosine transformation is applied, and after that we get our Mel frequency spectrum coefficients. Now generally, first 13 coefficients are used since they correspond to slow varying components in the spectrum. So in this study, first 13 Mel frequency spectrum coefficients were considered. Besides that, derivatives and double derivatives of these Mel frequency spectrum coefficients were also considered. After extraction of these features, we have used a support vector machine classifier which is used to classify these audio files into the 7 different emotions. Now coming now now coming to the fundamental frequency feature. Now coming to the other feature that we have used and extracted in our study is the fundamental frequency. The fundamental frequency in a signal can be defined as the lowest partial. For fundamental frequency estimation, we have used YIN estimator algorithm. The YIN estimator is an time domain pitch detector algorithm. Fundamental frequency carries information about the linguistic characteristics like the consonant voicing, sordic features, etc. Besides that, studies have shown that the fundamental frequency changes depending upon the emotion of the speaker. It was also observed in one of the studies that the anger emotion showed higher fundamental frequency than that of the neutral emotion, while the average fundamental frequency of the sorrow was lower than that of the neutral emotion. The study also showed that the average fundamental frequency of the fear was less than the anger and was more close to the fundamental frequency of the neutral emotion. Thus, keeping in mind the above observations and the factors which were which were observed in the previous studies, the fundamental frequency is taken into the consideration in this study. And for the via an estimator algorithm that was used for the extraction of the fundamental frequency in our study, we have used this algorithm with the help of the Librosa library of the Python 3. Now, after the after the brief discussion of the features, now we will come to the methodology part of the presentation. The feature extraction has been done using the Python. The classifier used for the comparison is the support vector machine. Support vector machine is a classifier which can be used for both binary as well as multi-class classification. In support vector machine algorithm, the algorithm finds a hyperplane that can correctly separate two classes with a maximum margin. In support vector machine, we have used various kernels such as RBF, sigmoid, linear, etc. in the study. The data set that we have used for the classification is the EMODB data set. The EMODB data set is a German emotional database. This database consists of various audio files that were recorded by a total of 10 speakers. The audio was originally recorded at 48 kHz and is then resampled down to 16 kHz. This database consists of 7 emotions, i.e., anger, anxiety, boredom, happiness, disgust, sadness, and neutral emotion. In this study, we have tried to classify all these 7 emotions. The features which is used in the study, i.e., frequency cepstrum coefficients and the fundamental frequency, were first extracted from the audio files and were normalized. Then the model was first trained on frequency cepstrum coefficients and then on fundamental frequency for optimization and the selection of the appropriate kernel function for the models. The grid search CV algorithm of the scikit-learn library was used. Now coming to the result part of our study. Now in this study we have used the following kernel functions in the support vector machine classifier. It is the linear, polynomial, RBF and the sigmoid kernel function. These kernel functions were used in both the cases in which the first case was when the model was trained using the MFCC and the second case was when the model was trained on the fundamental frequency. In case of the linear kernel function, the accuracy in case of MFCC was 69.6%, and in case of fundamental frequency it was about 26%. In case of polynomial, in case of MFCC the accuracy was about 71% and in fundamental frequency it was about 27%. For the RBF kernel, in case of MFCC the accuracy was about 72% and for the fundamental frequency case it was 27.7%. And in sigmoid for the MFCC the accuracy was about 68% and in the fundamental frequency case it was about 28.2%. Now by looking at all these accuracies in the table, we can clearly see that for the MFCC model or the frequency cepstrum coefficient model, RBF kernel function was taken as it gives the highest accuracy as compared to the others. And for the fundamental frequency model, sigmoid kernel function is considered because of the similar reasons as mentioned earlier. After the selection of the appropriate kernel functions and the training of the models, these were tested using the test data. Accuracy of the testing accuracy of the model with the MFCC is about 74.6%, while that of the fundamental frequency it is about 27.6%. Besides the accuracy, we have also observed and calculated the other metrics like precision, recall, and the F1 score. The precision of a model can be defined as true positives divided by the true positives plus false positives, and the recall can be defined as the true positives divided by the sum of true positives and false negatives. The F1 score in short can be defined as the harmonic mean of precision and recall. It can be observed in the table below that the average F1 score of the model of frequency cepstrum coefficient is 74.3% and that of the fundamental frequency it is 23.8%. Now looking at the ROC curves of these models. The ROC curve can be defined as the graph between the true positive rate and the false positive rate. For a model, when recall increases, there is an increase in the false positive rate. This increase in recall reduces the precision of model. Similarly, if precision of a model is increased, then there is a decrease in recall, false positive rate and true positive rate of model. When analyzing a ROC curve, which is a plot between two positive rate and the false positive rate of model, if recall increases, then the both true positive rate and false positive rate increases, which is obviously not good for the model. And if the precision is increased, then the false positive rate decreases, but true positive rate also decreases, which is again not ideal. Hence, just increasing recall or precision of model does not guarantee good performance and a good ROC area value. For a good model, both of the parameters, precision as well as recall, should have sufficient high values. This maintains a balance between the false positive rate and true positive rate, which ensures a good ROC curve and the area for the model. Mel frequency subsystem coefficient or MFCC model has its ROC area values lying in the range from 0.807 to 0.996, while for the model trained with the fundamental frequency, the ROC area values were lying in range from 0.411 to 0.802. With model trained with fundamental frequency, the worst ROC area result was for happiness, as its ROC area value is just 0.411. This value is quite less than the baseline comparison value of 0.5. This makes this classification worse than a random guess. For models trained with Mel frequency subsystem coefficients or MFCC, the worst ROC area value was for happiness, which is 0.807. The best ROC area value for MFCC was 0.996, corresponding to emotion disgust, while for fundamental frequency model it was 0.802, corresponding to sadness. An important observation to note here is that for emotions, sadness and the boredom, the ROC area value is high in case of the fundamental frequency model. This observation is quite important and forms the basis of one of the important conclusions of this study. Now coming to the analysis and the conclusion part of the presentation. Mel, it was observed that the model trained with the Mel frequency subsystem coefficient or MFCC overall performs better than the fundamental frequency in speech emotion classification. It was also seen that the RBF kernel for MFCC or Mel frequency subsystem coefficient and the sigmoid kernel function for fundamental frequency for SVM or support vector machine classifier gave good results for speech emotion classification. Another thing was that although the ROC area value of emotions in Mel frequency subsystem coefficient model or MFCC was more as compared to the fundamental frequency, It was observed that the ROC area values of the boredom and sadness, which is 0.791 and 0.802 respectively, of the fundamental frequency model were on the higher side. Thus, meaning that if the ROC area is the main criterion, then the fundamental frequency can be used for the boredom and the sadness emotion analysis. If this is quite a useful result as the size of the fundamental frequency vector, which is n cross 1, is less as compared to the MFCC vector, which is n cross 39, where n is the number of audio files. This reduction in the vector size reduces the computational complexity and thus can also save time. So with the previous slide of the analysis and the conclusion, this presentation comes to an end. Thank you.